Okay, so now we come to making things a bit more concrete when talking about these isometries. Okay. So what kind of things can we expect to, what kind of transformations can we expect to find as isometries? Okay. Well, if we consider first, so this is just a little lead in to this theorem 4.6. If we consider an isometry that fixes the origin, so it's got no translational part. It's just represented by multiplying by a matrix. Okay, because we had already that isometries are examples of affine transformations, so they can be put into this standard form here of multiplication by a matrix followed by a translation. So let's suppose that it's one that fixes the origin. So i.e., it is represented, it's represented by multiplication by a matrix A. Thank you. Multiplication by a matrix A. Now this matrix is going to be an orthogonal matrix. Okay, as we discussed last time. So the matrix A will be orthogonal. So A will have entries A, B, C, D. And being orthogonal will mean that the dot product of any column with itself is 1. So A squared plus B squared is 1. C squared plus D squared is 1. And the dot product of AB with CD, that's going to be 0. Okay, because those were the conditions of being an orthogonal matrix. So the vector AB is the image of I, of the basis vector I, under the isometry. And the fact that A squared plus B squared equals 1, this implies that AB is on the unit circle. So there's the vector AB. It's going to be somewhere on the unit circle. So we have a nice way of representing it in polar coordinates. We can say A is cosine of some angle theta and B is sine of this angle theta. Okay. Now similarly, the vector CD is also on the unit circle. And its dot product with AB is 0. So it's going to be at an angle pi over 2 to AB. So this implies then that C is going to be, because it's on the unit circle, we're going to be able to write it as cosine phi and D as sine phi. And the angle phi will be theta plus or minus pi over 2. Okay, because the vector CD has to either be coming out here or coming out here. okay? Because it has to be at right angles to the vector AB, because it's the image of the vector CD is the image of the vector I, sorry, of the vector J. And so I and J were at right angles to begin with, and so they have to be at right angles afterwards. Okay. But now, when there's a difference of pi over 2 between two angles, that means we're able to relate the cosines and sines together, because pi over 2 is kind of the distance by which cosine and sine are out of phase. Okay. So that means the matrix A is either, so we have cosine theta, sine theta in both cases. And in the plus case, where we're adding on pi over 2, then the cosine phi, the sine phi are actually equal to minus sine theta and cosine theta, okay? Because in that case, phi is theta plus pi over 2. And in the other case, it's the sine is attached to the other part. It's going to be sine theta minus the cosine of theta. So for an isometry that fixes the origin, it has to be represented by an orthogonal matrix. So that means there's really only two types of matrix that can arise. The matrix A has to be one of these two forms, okay? And these are very clear geometric interpretations. This matrix is rotation by the angle theta anti-clockwise about the origin. You can kind of see that in the picture, because this case is where the vector CD is pointing up this direction. So you can see that I and J have just been rotated by the angle theta. And this one, what's this one? This one is reflection in the line through the origin. For which line? It's the line with angle theta over 2. Let's draw a separate little sketch for that. So in this case, we're dealing with, here's our x and y axes. I has gone to this vector here, and J has come down to this vector here. So what's actually gone on is that there's a, if we think of the line at angle, so that's supposed to be the angle theta over 2, half the angle by which I has moved by. So this whole angle here is theta. So then you can see that, yeah, this vector I, the vector I has been reflected to here, and the vector J, which is up here somewhere, this has undergone a reflection down to the vector CD here. So in the terminology of the previous diagram, this was the column AB, and this was the column CD. So that little discussion there tells us that really, when we're talking about isometries, we're really only talking about rotations and reflections. They're the two types of two geometric types of isometry. And those are for ones that fix the origin. Obviously, we can do these things. We can rotate and reflect away from the origin as well. And we'll come on now to discuss the various possibilities. So this leads us into Theorem 4.6. This leads us to Theorem 4.6 in the notes. Is this one here, which is the geometric classification of isometries. Has everybody got that diagram? Okay. So here's Theorem 4.6. It's the geometric classification of isometries. We're going to describe all the different types of isometries are in terms of their geometry. Just add a little bit in here. We're describing them, but also in terms of a geometric description, but also referring to their fixed sets. So we'll be considering their fixed sets. So, and we get this classification where we say there's 6 types. First type is the identity transformation. So that's just where everything stays in the same position. You're just applying the identity transformation. So the matrix of that is just the 2x2 identity matrix. Second type is all the translations. So if you're translating by a non-zero vector, translate by the 0 vector, that's the same as the identity, just leaving everything fixed. So translating by a non-zero vector p, well, they don't fix any individual point, because every individual point is going to move. But of course, if there's any line for type 2, if you're translating by the vector p, suppose this is the vector p, any line through the origin, which is parallel to p, as a whole geometric object, as a line, it's going to stay fixed, or it's going to be preserved. Okay. So translation by p preserves lines that are parallel to p. The third type we're going to have are rotations. Well, a special kind of rotation first, rotating by pi degrees. So doing a full half turn of the plane. And we're going to allow it to have the center of rotation to be any point C. So it only has one fixed point. That's the center of rotation. Every other individual point moves. But it's going to preserve any line that goes through the point C. Any line which goes through the point C, after you've rotated the plane a full half turn, it's still going to be the same line. Here's the point C out here somewhere. If you've got any line at all through the point C, when you rotate the plane a full turn, a half of a full turn around C, and that line is still going to be the same line. The individual points on it will have moved, apart from C, but the line as a whole is preserved. So that's just special types of rotation. Then we have case 4 is the other more general types of rotation. So that's where you're rotating around any point C through an angle theta, which is not 0 or pi. you're rotating by an angle 0, then you're not rotating at all. So that's just the identity transformation. Okay, and the notation we use for that is r square brackets vector c theta. So vector c is the center of the rotation, and theta is the angle. And then we have two types of reflection. So we've got reflections as we normally understand them, and then these other funny ones called glide reflections. Well, a reflection, so in case 5, a reflection q c theta, this is going to denote reflection in the line L, which passes through the point C and makes an angle of theta with the positive direction of the x-axis. Now, what exactly is that? Here's a point, here's a generic point C. And the axis of rotation is going to be this line, sorry, the line of reflection, the axis of reflection, if you like, is going to be this line here, where this angle here is theta. So the angle that the line makes with the positive direction of the x-axis, that's the angle theta there. And so this QC theta is the reflection in that line, okay? So a point out here, a point, a generic point x out here will get sent to this point here, which will be QC theta applied to x. Okay, the whole plane gets reflected in that line. Now, what kind of fixed sets or preserved sets does that transformation have? Well, every point along the reflection line is fixed. Okay, because if you're already on the reflection line, then when you reflect the plane, that point is still at the same position. So it fixes every point on the line, and it preserves, as a whole, every line which is perpendicular to the axis. So if you have a line, another line perpendicular to the axis, after reflection, it's still going to be the same line. But if you have a line which is not crossing the axis in a perpendicular fashion, then after you reflect, it will go to a completely different line. Okay. Then lastly, we have glide reflections. And glide reflections are where you reflect the plane in a certain line and then follow it by a translation, but where the translation is in a direction parallel to the line. Okay, so let's draw this. Here's a generic point C. There's the line of reflection. So let's track a point X here. So we also have in the picture a vector, which is the glide vector G, and that has to be parallel to the axis of reflection. So I've drawn that so that it's parallel to this line. So QCG theta, when you apply that to x, you first reflect it. So when you reflect it, x will come down here, and you then translate it by g. So it will go to this point y here. Where this vector here, this translation vector there, is this same vector g. So you reflect the plane in the line, and then you slide it in a direction parallel to the line. So glide reflections don't fix any points. Every point moves to a new position, and it also changes every line except the line of reflection itself. So this line of reflection itself, which is called L here, in item 6 there, that whole line is preserved because the line doesn't move at all under reflection, and then when you shift it by the translation vector g, you're just kind of shifting the line along its length. As a whole geometric object, it's still the same line. Okay? Because the line goes on, the line goes on infinitely in both directions. So if you shift it in the direction g, because that direction is parallel to the line, it's still the same line. Okay, so this is our classification of isometries according to their geometry. So every isometry fits into one of those six types. Okay. So that kind of tells us what they are. What's the range of possibilities. The other thing we then need to know is how to work with them, how to perform calculations with them, and how to track the effect of applying multiple isometries one after the other, how to compose them and to recognize the effects of the compositions into one of those six geometric types there. Okay. So that brings us on to this section 4.7. And also the aim is we're going to be returning to these standard forms. Okay, so we take this expression for any kind of transformation, but for our isometries in particular, this expression of the linear transformation part followed by the translation part, that's our standard way of referring to transformations. Okay, so the idea is if we take an inverse or we perform a composition, we'll often be interested in bringing it back into this standard form. So we're going to look at a kind of a whole set of equations now, at a kind of a toolbox of equations. But just to set up some notation, so we've introduced this r square bracket and q square bracket notation here. So r square bracket c theta is the rotation about the point C by an angle theta, and q c theta and q c g theta are the reflections and glide reflections, respectively, through the lines which go through the point C and make an angle with theta, make the angle theta with the horizontal direction. Okay. Well, we're just going to slightly shorten that notation in special circumstances. In the circumstances where you're rotating about the origin or you're reflecting in a line that goes through the origin itself, we'll just omit mentioning the origin as the vector. We'll just simply write r theta or q theta. So r theta means rotation about the origin by the angle theta, and q theta means reflection in the line which goes through the origin and makes an angle theta with the x-axis. Okay, that just shortens some of the equations. And we'll also make the agreement that we'll leave out the composition symbol, the circle composition, function composition symbol. So all these equations here, you see we're putting these transformations beside each other all the time. Well, so you have to imagine that in between every pair of transformations there's a composition circle symbol. But we'll just, the same way that when you're multiplying together variables, you don't always write a multiplication sign, you just put the two variables beside each other. That's the same, similar idea here, okay? So there's various kind of equations that we'll need to use and need to be able to refer to here. The first set of them are ones that will allow you to handle all kinds of compositions that you have. Okay, so some of these we've seen already. If you, roll the screen on. If you compose two translations, well, we've already seen that that's the same as just translating by the sum of the vectors. If you compose two rotations about the origin, you rotate it by this much, and then you rotate again by another fixed amount. Well, that's the same as rotating by the sum of the two angles. Yeah. these are both rotations about the origin. So you rotate by an angle phi first, then you rotate the plane by an angle theta. Well, you may as well have just have rotated it by theta plus phi. Okay. Compositions of reflections isn't, it takes a bit more of an explanation and a sitting down with diagrams and plotting things out to see this. But if you reflect in the line with an angle phi, and you follow that up by reflection in the line with an angle theta, well, when you do two reflections, the result is a rotation. And you're rotating by the angle which is twice the difference, theta minus phi. So theta is the second reflection minus the angle of the first reflection, phi. So it's well worth your while sitting down and, plotting out two reflection axes, tracking what happens to a few points, and, satisfying yourself about that. And then we have two equations which tell us how to compose a reflection with the rotation in either order. And in both cases, composing a reflection with the rotation again gives you a reflection. So in the first case, where you reflect in the line with angle phi, and you follow that up by rotating by the angle theta, that's the same as reflecting in the line which is at an angle phi plus a half of theta to the origin. And if you do it the other way around, if you perform the rotation first, rotating by the angle theta first, this is equation 4.5, rotating by the angle theta first, followed by reflection in the line with an angle phi, that's the same as reflecting in the line with angle phi minus a half of theta. Okay. So we know how to compose translations with translations, rotations with rotations, reflections with reflections, and rotations with reflections. The only things we haven't covered there are composing translations with rotations and translations with reflections. But we've already seen that. So that would be this kind of setup. So we've already looked at this result. If you translate first and then apply a linear transformation to it, and the rotations R and reflections Q are examples of linear transformations, you can push the translation through the linear transformation, and it pops out the other side as translating not by P, but by f of P, okay, where f is the linear transformation. And the f is unchanged. The f is still the same, a linear transformation. Okay. So then there's a set of equations which take the rotations and the two types of reflections. Now, in general, these are going to be located at points other than the origin. And these equations here show you how to bring those into standard form, okay? Because the last expression in each case is always one of the standard form expressions. It's the linear transformation followed by the translation. Okay. Let's just look at the rotation one here. This is equation 4.7. So rotating about the center of rotation C by an angle theta, so this point here moves to this point over here, and you're rotating the whole plane by this angle theta. Well, as an intermediate step to bringing that into standard form, you see, C is the fixed point of the translation. Now, as I said in the previous hour, if you think about zooming out of that diagram, to a million miles away, the fact that this point C is not at the origin becomes insignificant, okay, because this distance will be tiny when viewed from very far away. So rotation, this rotation here is really just rotation by the angle theta. So as long as we can re-express this in a different way using rotation by theta, but keep c as the fixed point, then we'll have the same thing. So one way to do that is to first translate by the vector minus c. And what's the effect of that? Translating by the vector minus c moves c back to the origin. So that'll be rotation. That'll be this rotation here. That's translation by the vector minus c. So that'll take this point up here and move it down to approximately here. We then follow that by rotation by theta about the origin, which will put this point to approximately here. But then you translate again by the vector c, and that pushes this back up to where it's supposed to go to. Okay. So if you want to rotate the plane around the point C, first you kind of drag the plane so that the point C moves to the origin. Then you rotate around the origin and then push the plane back so that the origin moves to C. So in total, C goes to C. Because if you track what happens to C by each of these three things, the first translation moves C to the origin. The rotation rotates the plane around the origin, so the origin stays fixed. And then we translate by the vector C again, which moves the origin back to C. Okay. But then to put this into standard form, well, we've moved some of the way here because we've isolated the linear transformation part. Rotation by theta is now rotation about the origin by theta. Where my finger is, that's now linear transformation. We've got a translation to the left of it. That's fine for standard form, but we've got a translation to the right of it. So we want to push that through, drag this rotation on the right through the translation on the right there, back through the rotation. And using the results that we've looked at already, this is going to come back as translation by the vector, which is the rotation applied to minus c. And then the rotation r theta is left there. And tidy that up a bit, rotating the vector minus c is the same as minus rotating the vector c. So in total, you've got translation by c minus r theta c. And doing that after rotating by theta. So this is in standard form. Okay. And in a similar way, the other equations on that page take the reflections, the two types of reflections, reflections and glide reflections, and show you what their standard forms are. The standard form in 4.10 for a reflection, QC theta, bears a lot of similarity to this standard form for the rotation. It's reflection in the line through the origin with angle theta. That's this first part, Q of theta here, which is applied first. And then the translation, which you need to do to correct for the fact that C isn't at the origin, is just translating by the vector C minus Q theta Z. Okay. And the glide reflection case is just a bit more of a mouthful, because there's really, there's going to be more vectors involved because you've got this glide translation vector. But the standard form for that shares a lot of similarities as well. Okay. So maybe we'll do exercise 4.5. I think there isn't really much to it. what are the inverses of these things? What's the inverse of a rotation? What's the inverse of a reflection? And what's the inverse of a glide reflection? Well, what's the inverse operation to rotating the plane about the point C by an angle theta? Well, you just have to undo the rotation. You just have to rotate it back. So you're still going around the same center, but this time you're going through an angle minus theta. You're simply undoing the rotation. How do you undo a reflection in a line? You have some line going through a certain point, C, and you reflect the whole plane in that line. How do you undo it? Well, you kind of want to reflect it back, but that's just exactly the same operation. So with this one, it is its own inverse. So a reflection is its own inverse. Okay. A rotation isn't a rotation, well, except for the special rotation, which is rotation by pi. If you rotate the plane 1/2 of a full turn, well, if you just do that again, you get back to the identity. So that's its own inverse. But in general, rotations aren't their own inverses, as a normal reflection always is. And a glide reflection, well, if you think what happens by glide reflection, you reflect a point first, and then you glide it by a certain amount. So x is reflected in the line and then glided by a certain amount. Well, to get that point y back to x, you could just reflect it in the line again and then glide it back by minus g. So we can use the same reflection, but gliding now by an angle minus g. So we have the geometric classification into the 6 types. We have the notation, r square bracket, q square bracket, for the rotations and reflections. We have this bunch of equations now which can allow us to compose them in any way and always return back to standard form. Okay, so those are the ingredients that you're going to need basically for assignment 3. But we'll finish off just going to the last page in the notes. When I see you on Monday, we'll do more. We'll do some more examples. We'll do some example problems, which are kind of in the same spirit as assignment 3, or a similar spirit, just to help you be thinking in the right way for those. So just look at the last page of the notes here. Well, we've already really covered the matrix forms. We saw that earlier, the matrix form for rotation and the matrix form for a reflection. So we covered those at the start. Then we got this last little section, 4.8, which is a little kind of a, well, it's kind of just a kind of, as far as we're concerned, it's a kind of an organizing trick. So it's this idea of homogeneous coordinates. Well, it's not really a problem, but one unfortunate aspect of what we've developed so far is we've got all these wonderful isometries here, or let's say these ones appearing on this page. So we've got all these objects that we're working with, and we can represent them all with matrices, but except for the translations. So the translation, so every, all the reflections and rotations there, appearing up here, we can represent them all with matrices, except for the translations. So just for organizing things and for implementing things on the computer, it'd be nice if it was more consistent, if translations could be represented by matrices as well. But of course, they can't. So if you think about it, if you have any matrix, a consequence of matrix multiplication is that a matrix multiplied by the 0 vector is the 0 vector. And there's no getting away from that. We can't, we can't change that. We certainly don't want to start introducing a new type of matrix multiplication or anything. That won't solve the problem for us. But there's a neat little trick. If we introduce a new coordinate. So up to now we've just been, we refer to points in the plane with a pair of coordinates, because that's all you need. Distance along the x-axis, distance along the y-axis. Well, if we allow ourselves to add on an extra third coordinate. Now, in terms of locating the point, so we're going to call this third coordinate s, x, y, s. Most of the time, we'll just ignore it. And we'll consider the point x, y, s to just be the point x, y in the plane. But the fact that it's sitting there means that we can represent translations using matrices, okay? And that's this by this way here. If we have homogeneous coordinates for the point x, y, and if we have the third coordinate s as 1, so that'll be the standard way of representing a point in homogeneous coordinates. So a point in the plane will have homogeneous coordinates x, y, 1. Then, when we multiply it by this matrix, this will have the effect of translating the point by the vector p. P is p1, p2. Okay? Because if you do that, here's the matrix. If we multiply that by the column vector x, y, 1, the fact of having the 1 here and the 2 components of the translation vector here, when you multiply that out, you get the vector x plus p1, y plus p2, 1. So you get exactly the vector x, y, 1 translated by the vector p1, p2. So just by this little trick of adding in a third coordinate and making it 1, suddenly now we can handle translations as using matrices. The homogeneous coordinate matrices for rotations and reflections are just more or less the same as they were, but we just add in 0, 0, 1 as an extra row and column in both cases. And we can also handle rescalings, though. Now, rescalings, of course, are not isometries. Because they obviously change distances. If you rescale the plane by shrinking or growing, you're obviously changing distances. But they are useful transformations to use when we're assembling virtual environments. Okay. Okay. So this is how we're going to work with these isometries in the plane. And when we put them on the computer, we're always going to use these homogeneous coordinate representations so that we can treat everything in a consistent way. And every transformation can be represented by a matrix. The rotations, reflections, and the translations. Okay? And it's not just done for kind of style, for ease of use. It actually has real consequences in terms of the hardware and that. So you're familiar with things called graphics cards. If you're into computer gaming, you've probably gone out and spent loads of money on specialist graphics cards or upgraded your graphics cards. Well, one thing these graphics cards do is they implement in very specialized hardware, specialized chips that are built to be especially efficient at performing matrix multiplications so that they can transform all the elements of the virtual environment around really, really quickly and render things, get everything in the right place and produce it onto the screen extremely fast, okay? And so it helps for them if everything can be represented as a matrix. If rotations, reflections, and translations can all be just fed through this same specially designed hardware, which is specially designed for, well, one aspect is at least to doing matrix multiplication extremely quickly. Okay, so this kind of sets you up for assignment 3, and on Monday we'll do some, we'll have a look at assignment 3, and we'll do some helpful examples and example problems. Okay.